Assistant Professor Urmi Shah from IT/ICT Department of LG Institute of Engineering and Technology. Today we will be starting with the second chapter, that is noise in analog and digital communication system. So up till now we have seen what is basically noise, what are the classification of noise, what are the sources of noise, from where noise is created, what is internal noise, what is external noise. Basically in our communication system, when noise signal is generated, that we are going to see in this session by doing its theoretical analysis of all noise sources. So let's start with this chapter. So in this module, we will be seeing is the noise calculation, what are the formulation of noise, then we will be seeing is the noise factor, and then we will be having the next topic, that is noise figure. So what are all these parameters that we will be seeing in this session. So basically we have seen the basic calculation of noise in the previous session, that if we have thermal noise, then it is due to the temperature variation or temperature effects of solar noise. So basically this thermal noise or solar noise is having the formulation of energy radiated or heat energy produced basically due to this noise is formulated as En is equal to 4R kTB. So this noise formulation is having En as root mean square noise voltage. So this is the parameter of calculating the noise voltage. Then in the formulation you can see 4 is the numerical value, that is number. R stands for resistance of conductor. So basically if you have one conductor and inside that conductor if the amount of heat rises in form of temperature, then the noise created in this temperature that we are going to measure by this formulation, that is En is equal to 4R kTB. En is your root mean square noise voltage, that is measured in volts. R is your resistance of conductor, that is measured in ohms. T is the temperature rise in the conductor, that we have in Kelvin. And Bn is the noise bandwidth, that is the range of frequencies where the noise is going to be created. So Bn is the noise bandwidth, that is measured in hertz. K is the Boltzmann constant, which is having value 1.38 into 10 raised to minus 23 joule per Kelvin. So this is the formulation of noise, and this is the formula if you want to calculate the thermal noise. Now the next kind of calculation in this category is of noise power. Up till now we have seen is noise in voltage. Now if you want to calculate the power of noise, then the formulation is like this. En we have calculated, that is En is equal to root of 4kRTB. Then if you want to calculate power, basically what is power? Power is multiplication of voltage and current. P is equal to voltage into current, V into I. And instead of I, if you want to use the formula of voltage, then we can have the Ohm's law formulation, that is V is equal to IR. So I can be written as V upon R. So the whole formulation of power is like this. P is equal to V square by R. So V square by R, instead of V we can have the value of noise voltage. So after whole formulation, the formula of noise power is equal to kTBN. K is your Boltzmann constant, T is your temperature, and Bn is your noise bandwidth. So this is the formulation for noise power. Now next we will be seeing is the formulation of equivalent noise bandwidth. Basically, any parameter if you want to define in terms of noise terminology, then we have to calculate its equivalent value. Now, what is this equivalent value? That we will see. If you have a transfer function for any communication network, let's take an example. H of f is the transfer function of network which is having some resistance R. So the spectral density is the overall density of your communication system in terms of voltage or mean square voltage will be equal to 4R kT H of f whole square. Now H of f is your transfer function which is present in your communication network. H of f is the ratio of output to input voltage for mean square voltage. So basically it will be unitless. H of f is the ratio of output voltage upon input voltage. So this is the formulation for equivalent noise bandwidth. Now the next if we want to see is the noise factor. Basically on which factor we are calculating the noise, that we will be seeing. So let's have a look on noise factor. Before noise factor, we need to understand what is the signal to noise ratio. Basically, what is the meaning of signal to noise ratio? If I am transmitting some signal from one end to another end and that signal is transmitting without any error from one end to another end, then the signal to noise ratio ideally will be 1. That means this signal has been transmitted without any noise, and if this signal is having some interference of noise, then it will be always less than 1. So ideally signal to noise ratio should be 1, which indicates that whenever we are transmitting any signal from transmitter end to receiver end, there is no noise introduced in that channel, and ideally that signal which was transmitted is received originally at the receiver end. So SNR ideally should be 1, but generally it is always less than 1 due to introduction of noise in every communication system. So it is formulated as ratio of signal power upon noise power. What is SNR? SNR is the ratio of signal to noise with respect to noise, how much signal is transmitted from one end to another end. So SNR ratio tells us the amount of noise introduced in signal transmission. So it is having the formula as signal power upon noise power, or signal voltage upon noise voltage. So SNR is having the formulation PS upon PN, that is signal power upon noise power, and VS upon VN, that is signal voltage upon noise voltage. So this is the formulation of SNR, that is signal to noise ratio. Now the next is noise factor. Based on the SNR, we will be able to understand what is noise factor. Noise factor is the ratio of available SNR at the input side to the available SNR at the output side. Let's take an example. If I am transmitting one signal from transmitter end to receiver end, then at the transmitter end, whatever the SNR will be available as an input, the ratio of that input SNR upon the ratio of the output SNR, that is your receiver end SNR, is known as noise factor. So noise factor is the ratio of input SNR upon output SNR. Now let's take an example that if you are transmitting any signal, then that signal will be having some input power. So that is your input power P and I, that is your noise input power, that is formulated as KT0VN. K is your Boltzmann constant, T T is your temperature. At room temperature, whenever we are transferring any signal or transmitting any signal, T0 is your room temperature, that is 220 Kelvin. Bn is your noise bandwidth, the range of frequencies where we are transferring our signal. So that is your noise bandwidth. So PNI is equal to KT0Bn. K is your Boltzmann constant, that is 1.38 into 10 raised to minus 23 joule per Kelvin. And Bn is measured in hertz, that is your equivalent noise bandwidth. So this is the formulation of noise factor. Now if I want to describe it in detail, then input side SNR is PSI upon KT0B. Basically what is SNR is signal power upon noise power. So signal power is PSI, input side signal power, upon KT0Bn is your input side noise power. So noise factor here can be defined as input side SNR upon output side SNR. So the formulation will be like this: PSI upon K T0Bn upon PSI at the output side will be having some output gain which will be multiplied. So GPSI upon PN0. So whenever this term will go in the numerator, the whole formula will be like this, that is noise factor F is equal to PSI upon KT0Bn into PNO upon GPSI. Basically G is your power gain, overall power gain. So that's why your output power will be G into your input power. G is your power gain. So the overall formula for noise factor will be PNO upon GKT0Bn. So this is the formulation if you want to calculate noise factor for any communication channel. Again, if the output noise power is having value PNO, and if you want to calculate the output power or output noise power from the noise factor, the formulation is revised as PNO is equal to F into G into K into T0 into Bn. F is your noise factor, G is your power gain, overall power gain, T is your temperature, K is your Boltzmann constant, and Bn is your noise bandwidth. So this is the formulation of noise bandwidth, which actually depends on input power delivered to the amplifier. So that is your output power. Noise factor is the factor which decides the amount of noise introduced from input to output side. So this is the noise factor. Now the next is noise figure. Noise factor was measured initially, which was having no quantity. That means it was unitless. It was input SNR upon output SNR. So it was basically measured in decibel. So the noise figure is the revised formulation of noise factor, that is measured in decibel, that is equal to 10 log of F. F is your noise factor. So this is the formulation of noise figure. One of the example has been shown here is if the noise figure of an amplifier is 7 dB, and if you want to calculate the output SNR ratio and input SNR is given to you is 35 dB, then how we will calculate the output SNR? So the formulation is noise factor is basically output SNR and input SNR ratio. So it is input SNR upon output SNR. So you will find out output SNR by subtracting the noise factor from input SNR. So 35 minus 7. So 28 dB will be your output SNR ratio. So this is about noise figure. Now this is the overall block diagram of amplifier signal having input noise in terms of noise factor F. So basically PNI is your input noise power, PNO is your output noise power, and G is your overall gain, overall power gain. So PNI is equal to PNO upon G. So this is the formula if you want to calculate input noise power. PNO is F into K into T into Bn into F. So that will be cutted, G will be cutted, and the overall formula for PNI will be F into K into T into Bn. So PNI is the multiplication of noise factor, Boltzmann constant, room temperature, and noise bandwidth. This is the formulation for input noise power. So this way we will be looking upon various noise calculation in the upcoming session in depth, and we will be looking upon some of the numericals and examples from which this topic can be frequently asked in your exam. So this is all about noise calculation. If you want to refer the topics, you can refer this reference books for this topic, which we have covered in today's session. Thank you very much for watching this session. In the upcoming sessions, we will be discussing various examples based on the noise formulas which we have discussed today, and we will have one derivation on calculation of noise for some cascaded communication system. So thank you so much for watching this session.